Good morning, everyone. This is John Chappell, Natural Philosophy Society Science Chat. I am your host, Franklin Hu. And today we have the topic of quantum entanglement. So we have James Keene here today. And he had some slides he wanted to show us about quantum entanglement. So I think you can go ahead, James, and try and share your screen, and I'll let you take it from there. All right?
Okay. Okay, now.
We talked a little bit about quantum entanglement last week, but you said something had something to do with time phase or something, right?
Yeah, I'm trying to get the screen to share. It says share.
There's a couple things you have to click.
Share.
After you click on share, then you actually have to click on the middle of the dialogue on the little picture of your screen, and then click share.
Oh, there. Yeah, I got it. Thank you.
Okay, now we got your screen here. No, that's not your screen yet. I should see your, yeah, I got James Keene's screen. Okay, so I'm going to add that.
This is my screen. View slideshow.
Yeah, there we go.
There, do you have it?
We can see your screen now.
Oh, okay.
Okay,
I've got 11 slides here. This one is just sort of a fun slide of what it looked like when CERN announced the discovery of a new elementary particle recently. Now let's see if there. All I got to do is click, and here we go. Okay, this is from the Bell inequality violation myth debunked article. The myth that the Bell, I don't know if you can see my cursor here. The myth that the Bell inequality. You can see the cursor?
Yes.
The myth that Bell inequality violation establishes superluminal causality is debunked. Entanglement experiments designed to demonstrate non-local effects apparently all rely on Bell's theorem, also known as the Bell inequality. So here we're going to get into the real nitty-gritty of it. However, Bell himself stated, quote, "There is a way to escape the inference of superluminal speeds and spooky action at a distance." That's a phrase that Einstein, of course, coined because he didn't like this spooky action at a distance. But it involves absolute determinism in the universe. Therefore, according to Bell, the exact time development laws called bit operations in binary mechanics prevent particle entanglement experiments from demonstrating non-local spooky action at a distance. This inescapable conclusion debunks the myth that the Bell inequality can be used in entanglement experiments to demonstrate superluminal effects, and implies that quantum mechanics assumptions that system time evolution is fundamentally probabilistic, in other words, not exact, are questionable. In short, use of the Bell inequality in entanglement experiments acts to establish that legacy quantum mechanical formalism has been hopelessly flawed, no doubt including the unjustified assumption of continuous space-time. Now, here's just a little funny figure. The unintended result surprises investigators. Legend: the believers in superluminal causality face their worst nightmare caught in the headlights of binary mechanics. What do we mean? Let's go on. If theoretical physics was not presently embroiled in so many dead-end streets, observation that an object such as entangled particles may maintain properties over time might be considered as little more than a trivial fact. A poster child example of such dead-end legacy theoretical physics may be the saga of experiments using entanglement to show violation of the Bell inequality and, by implication, so-called instantaneous action at a distance. Indeed, this saga might rival string theory in triggering the when all else fails rule, finally leading to consideration of other alternatives or assumptions, such as those in binary mechanics. So let's get into it. In the famous 1935 EPR paper by Einstein, Podolsky, and Rosen, a paradox was presented that most listeners here are probably familiar with to support the possibility that a physical theory implementing local realism might be described in the future. We're now in the future. Some 60 years later, the 1994 paper on binary mechanics did exactly that, defining time development laws. With quantization of space-time and energy, the infinitesimal operators of quantum mechanic formalism and using the standard model were no longer applicable, since only integer increments in position, space, and time, quantized ticks of time, were allowed mathematically. For mathematical consistency with quantized space and time, 4-bit operations were developed, a pair of relativistic Dirac-Spinner equations of opposite-handedness, eliminating uncertainty in how any physical system evolved over time. Now, this is revolutionary stuff, folks. Listen carefully. Binary mechanics is local insofar as all actions occur over a distance d in one time tick t, where d and t are the fundamental length and time constants respectively. I now call those capital L and capital T in italics in more recent papers. Hence, the maximum non-locality in spatial position is length d in time, and in time is the interval t. Otherwise, binary mechanic locality is thought to be consistent with local relativistic causality. The realism component in binary mechanics asserts that one-state bits, which I call quanta, in a system state exist whether they are observed by people or not. Now, here is our freedom loophole. As a credit to the intellectual honesty of investigators using entanglement paradigms to test the Bell inequality, there is general agreement that reported violation of local causality might be explained by a so-called freedom loophole. On the other hand, this possibility, the one postulated by binary mechanics in 1994, is disparaged as much as possible, perhaps to justify the enormous effort to remove all loopholes, allowing alternative explanations of these experiments, the Bell inequality entanglement experiments, over many decades. Thus, the freedom loophole has been characterized as super deterministic, non-freedom, yuck, absolute determinism, yuck, implausible, quote, loss of freedom to choose, unscientific, and the like. In other words, there's been propaganda against it. Why is such extreme language used in physics literature and commentary? I thought physics was supposed to be just some math equations and some friendly talk. Not just deterministic, but super deterministic. Not just raising questions about freedom, but non-freedom, yuck. Not just determinism, but absolute determinism. Well, what's the difference? Not just difficult to imagine, but quote unquote implausible. Not just raising questions about free will, but, oh, horrible, loss of freedom to choose. Not just posing new questions in science, but quote, unscientific. They're really threatened by binary mechanics. You can see that. The need for such melodramatic descriptions is simple, namely that entanglement experiments alone cannot eliminate the freedom loophole. That's in boldface. Let's say that again. Entanglement experiments alone cannot eliminate the freedom loophole. Instead, any viable local realism theory must itself be falsified. You have to falsify binary mechanics in order to get your action at a distance. In the absence of experiment, undermining the veracity of binary mechanics is the leading local realism theory. The extreme language may be little more than a sort of propaganda ploy, quote unquote. Believe in superluminal effects shown by Bell inequality violation, or you are an anti-freedom jerk and get out of the room. Right? Such propaganda, that's what it is, may obscure the fact that loophole-free entanglement experiments showing superluminal causality may be impossible in principle. Now, what are the superluminal causality issues? I've listed 8 issues and we're done. Unfortunately, believers in the Bell theorem that no theory, such as binary mechanics, can reproduce all the predictions of quantum mechanics may have several problems. One is in inapplicable math. More frequently, as finer levels of detail are examined by the outstanding experimentalists in the physics community, researchers appear to be encountering defects in quantum mechanic predictions. If this is true, one would not want to reproduce all quantum mechanic predictions, making this nutshell version of the Bell theorem inapplicable or irrelevant. First, the quantum mechanic wave function misrepresenting position in continuous real number coordinates is only an approximation of actual positions where only integer coordinates are allowed with spatial quantization. Second, infinitesimal operators are quite simply the wrong math when position and time may have only integer values in the binary mechanic quantized space-time frame. Now, I know that a lot of the users here, our listeners here, like infinitesimal operators, they're involved in, for example, the calculus, which is used in physics quite extensively and so forth. Thus, at the finest level of binary mechanics, quantum mechanical predictions may be distorted or outright incorrect because of the 2 factors I just mentioned. As a consequence, the success of quantum mechanical formalism at the atomic level is becoming more difficult to duplicate at the nuclear physics level. Second, mandatory scientific disciplines. What is that? The exact time development laws in binary mechanics describe how any physical system changes over time given its initial state. The advantage of this exactness is that fudge factors like Heisenberg uncertainty need not be routinely considered. Another advantage is that scientific discipline is mandatory. For example, there are no excuses like, well, this was not predicted exactly, but Heisenberg uncertainty will save us. Even worse are QM predictions requiring Heisenberg uncertainty. Third point, deadly indeterminism. The exactness in bit operations implementation in binary mechanics also suggests precision, stability, and reproducibility. Think about that, precision, stability, and reproducibility. Would the reader prefer to remain intact in one piece as the human body speeds through space with the Earth at thousands of kilometers per hour with reference to the fixed star frame? Binary mechanics may be the only physical theory today that may assure survival at such velocities. Else, every instant would be a terrifying cliffhanger. Will I remain intact and alive or be splattered on the wall in billions of tiny bits of blood, sweat, and tears and tissue due to the wonderful intrinsic uncertainty in quantum mechanics? Close quote. Without the precision of the bit operations, similar to that seen in digital data processing, how could we possibly remain intact? The quantum mechanical thinking that this or that particle in our body might be here or there, or some probability to be everywhere, might be stimulating for the imagination, but deadly when it comes to survival. So this is sort of a anecdotal point 3 here, this deadly indeterminism. How about the philosophy in physics? The physicists have failed at their own craft physics, and yet we are expected to think that their philosophical ideas can make any sense at all. A recent report described the possibility of two relevant frames. In the binary mechanical spacetime frame and to the observational frame. If these two frames are not identical, hypotheses in the observational frame, that's what we observe every day, can be tested in binary mechanics simulations as long as length and time values can be projected from one frame to another. I'm going to skip down here. A fact of present interest is that sentient humans are embedded in the observational frame. Thus, physicists might show some care to conclude that they, as entities embedded in the observational frame, might necessarily be fairly characterized as lacking freedom to choose or free will. This is physicists trying to be philosophers, based only on exact time evolution laws in the binary mechanical frame. Such a causal mixture of science and philosophy may not be warranted. We're almost done. This is point 5 of 8. Up-down spin mechanisms. Entanglement experiments using up and down spin have apparently not clearly considered the recently described physical mechanisms involved and their implications regarding purported Bell inequality violations. This analysis identified two factors determining an up-down spin or polarization result. First, the particle time phase, and two, the elementary electromagnetic resonance. First may be considered as a particle property which might or might not change over time and which is local to the particle at its location. The second, resonance factor, depends on time parity. In other words, are we on an even or an odd tick, namely the odd or even parity of a tick interval equal to the 4 ticks t required to implement each of the fundamental bit operations, of which there are 4. In particular, after an odd or even tick cycle, the EM resonance state is thought to be similar throughout all space to the previous tick of the same parity. Therefore, spin measurements made at distant locations in the same tick interval or parity might share this factor in spin or polarization measurement results to some measurable extent. Without consideration of this recent work in 2015, descriptions of entanglement using up-down spin or photon polarization may appear somewhat primitive, omitting completely the second factor of elemental EM resonance. I have a slide on this if there's interested, but I'll just proceed on with this list here. Inaccurate local realism formalism. Point 6. The derivation of Bell's theorem, if you go back to the math, assumes a local probability space. A local probability space. However, there's no such thing in the binary mechanics spatial frame. At any time tick t, the system state is entirely described by the bit function, a quantized update of the QM wave function, where each bit locus is definitely in either a 1 or a 0 state. That is, a bit locus is either 100% or 0% probability in the one state. Thus, binary mechanics may deprive the Bell theorem of one of its two fundamental assumptions. Poof, no Bell theorem anymore, gone. Implied anthropomorphism. Here's another sort of intuitive point. Believers that Bell inequality violation in quantum entanglement excludes local realism and includes superluminal effects, things going faster than the speed of light, for example, may sometimes tend to explain all this subject matter in terms of particles as little people. What the particle knows is often discussed. And when it knows it, this tendency may not be a critical issue, but it can be annoying or distract attention from real critical issues, okay? In contrast, binary mechanics postulates abstract spatial objects of finite size, which may contain abstract binary one-state bits of energy, the bit function system state, and which contain physical mechanisms able to implement the fundamental bit operations in 4 tick cycles. None of the spatial structures, physical mechanisms, or binary bits need to know anything. They're not little people, folks. And there's the analog angle assumption. Franklin will like this one. Basically, when you quantize space, I won't read the text here. You know, all angles are actually a ratio of two digital values, or three, if you want to talk about an angle in three dimensions. So here's the end. Bell inequality violation, and hence its interpretation as superluminal effects with instantaneous action at a distance appear to be widely accepted in the physics community. Yes, they are. Indeed, investigators are apparently working on experiments to demonstrate such violations where almost all loopholes are filled. Almost all, but not all. However, which goes back to our first paragraph of this article. However, the present article argues that such work is not necessary. So you all can go home with any rationale whatsoever, since binary mechanics represents the so-called freedom loophole, which cannot be excluded by entanglement experiment, according to the entanglement people themselves. That's what they say, not me. Instead, freedom loophole elimination may require convincing falsification of binary mechanic postulates, in other words, quantization of space, time, and energy. At present, it may be fair to say that the entanglement work thus far showing Bell inequality violation tends to undermine some fundamentals in quantum mechanics rather than the local realism in binary mechanics. In other words, it's sort of backfiring. They're showing that their own work is being undermined by the results that they're getting. In short, while intending to achieve goal A, debunking local realism, this experimental work has resulted in achieving goal B, debunking features of quantum mechanics as traditionally run. Now, as our last little slide here, here's what you're going to have to falsify in order to have superluminal communication. Binary Mechanics Lab is the first ever to derive very basic constants for first principles. This makes it the winner of the century-long physics grand championship race. That one's going to be a tough one to knock down. Bit function defeats wave function 2-1. Why? Because both position and momentum are represented in the binary mechanical system state, whereas the wave function in quantum mechanics is only involves one or the other. So the people doing the entanglement experiments don't even have the best system state representation possible in physics to do their experiments. So they're really at a disadvantage. The bit operations defeat the quantum electro dynamics and the quantum chromodynamics for the best time development laws. Whoops, I clicked on something. Let's see, can I go back to that? Well, okay, I was just summarizing. Let's maybe stop sharing. There we go, we're back. Let's get this out of the way. So that's sort of like what my take is on quantum entanglement. Thank you for your patience, listening, and so forth.
So it seemed to me that binary mechanics is deterministic, right? I think that's the main thing, right? That things remain
That's
the
right.
same, and it doesn't matter if you're looking at it.
We don't say that the universe is dumb. That's what legacy quantum mechanics does. So the universe doesn't know where the particles are. It doesn't know what's going to happen. Its rules of time development don't tell you what's going to happen. In other words, the universe is dumb. It's sort of like that Michael Jackson song, which we are the world. We can
I don't know
change the title. We blame the world. That's what the quantum physicists do. They blame the world for their own ignorance.
Well, I don't know that it's dumb, but quantum mechanics makes this very strong implication that that it's not deterministic. That if I have an electron, that its state is undetermined, right? If something has some kind of state. So if I take my Lego model here, you know, it can be either facing this way or it can be facing that way.
Yeah, well,
And I
that's
think
our
quantum mechanics
observational
is saying that I
ignorance.
can't tell which way it's facing until I actually look at it, right? But that's that whole thing about the cat being live and cat being dead thing, right? That's
Yeah,
why that,
these are the fantasies of legacy quantum mechanics. I call it incomplete quantum mechanics because they fail to quantize space, time, and energy. So for some reason, they're happy to quantize a few things, but not able to quantize the three most important things that need to be quantized to bring quantum mechanics into what I call full quantum mechanics, which is the name for binary mechanics. So, yeah, I mean, what they've done is taken the Heisenberg uncertainty principle and basically say that instead of just being an observer effect, in other words, a limitation of the observer to determine the state of a particle because of the measurements that we do, it's actually a property of the universe. In other words, that the universe is fundamentally ignorant. And it's not us physicists that are ignorant because we've got the Heisenberg uncertainty principle. So we're very, very smart. But the other guy, the universe, and everyone else in it, even if they're alien creatures that are much more advanced than us, they're all completely stupid. So we, the physicists, were smart. Everybody else, including the universe itself, in which we are embedded, by the way, is dumb. It's a Michael Jackson song. I changed the title. We blame the world. Instead of we are the world, it's we blame the world. We are the physicists.
so that's the quantum mechanical interpretation, right?
Yeah. Don't admit we're ignorant about anything. We know everything, and it's the universe that is completely stupid. That is the legacy partial quantum mechanics. Once you quantize space, time, and energy, this nonsense is unavailable. You just simply can't go there.
Now, I did kind of my research on this yesterday, so you can find lots of information on this topic here. So let me share my screen. Let me just show you the things that I found about it. So, you know, you can find basic information about quantum entanglement on, of course, Wikipedia. And about, you know, what this whole controversy was about. Now, curiously enough, this has to do with Albert Einstein. Now, Albert Einstein basically disagreed with quantum mechanics in this, the basic idea that when you look at something, that actually changes its state. Because I think as far as I can see, the main thing with quantum mechanics is that the state of the thing that you're looking at is undetermined until you look at it. That's their main.
Well, it's undetermined in terms of our knowledge of it. It's not undetermined in any other way. It's just undetermined in our head. Okay.
Well, I think that would be your interpretation. I think that's a more deterministic interpretation, that if you have something, and let's say it has a property like it has a polarization phase or something, right? It's maybe right polarized, the beam of light's maybe right polarized. Our normal thinking would be to think that, yeah, it just stays right polarized. But in quantum mechanics, I think I might be getting this wrong, but literally the photon has neither, say, the left or the right polarization until you look at it. And then there's this thing called the collapse of the wavefront. And then that tells you what it is finally, right?
Yeah, so that is the fairy tale.
That is the idea that quantum mechanics so desperately wants to hold on to.
since they cannot deal with the specific issues, they have to make up fairy tale stories like this, like you just said.
Well, I don't know why they
And
make up
so if you
fairy
like the
tale
fairy
stories
tale
like
stories
that.
that a wave function collapses, like let's see, let me write down a wave function on a piece of paper and watch it collapse. What happens? The ink gets scattered around on the paper, or what happens when a wave function collapses? This is complete nonsense.
Yes, it does seem like complete nonsense, doesn't it? But
Yeah.
I'm just pointing out that this is what the quantum mechanic people want to so desperately believe in, that somehow their entire system is based on the fact that everything has to be probabilistic, and by probabilistic means that there's always a chance of something happening differently, right? So if I go and I look at a coin that's stuck on my table and it's heads, that there should be some probability that when I look at that coin, it's going to be tails, right? That's because everything has to be a probability, right? Nothing can ever
Again,
be.
you're talking about what you know in your head. You're not talking about the universe in which we live, which is what physics is supposed to be about. Now, I see here in the chat, Bob Gray has asked, what about the experiments of quantum computers and qubits that depend upon entanglement? These experiments are wrong. Well, I'm not up to date on those experiments. So, Bob, please answer that question for us.
You know,
Let
let
us
me see.
know.
Let's see if we can.
Are they wrong?
We've got a bunch of people. Why don't I bring everybody onto the stream here that's here? So we have Roger, we have Ian, we have Carl, we have Bob, and we have Bill. Okay. Well, let's see here. I can't add Bill because, let's see here.
And thank you for your patience, everybody, listening to my little presentation.
Got at least Bob here, right? Okay. So, Bob, go ahead and ask your question.
I don't really know a lot about quantum computers and the way that they do qubits, but it's my understanding that they entangle quantum mechanical, quote unquote, entangle various states to define a qubit. And they're making quantum computers. And so my question to anyone, not just James, is, well, then, if this is correct that you don't have these entanglements, then what's going on with these quantum computers?
Well, I don't
Now,
know.
remember, if I maybe jump in first to respond to that, my presentation did not say that particles cannot be entangled. In fact, what I was saying is that the properties of a particle can continue to have certain properties over time. What I was saying is superluminal communication, which is what some people are attempting to use entanglement experiments to show. Whereas Bell himself, in his Bell's theorem of Bell inequality, recognized that if you have local realism, and also Einstein in his paper that I discussed, and also Franklin just mentioned by going to the Wikipedia page, that that the local. So I'm not saying that particles cannot be entangled. Okay, there's no reason why they couldn't be. What I'm saying is that using entangled particles, if they are definable, as a way to show supraluminal communication is a falsehood, is debunked by the presentation that I gave.
Okay, thanks.
Even Einstein said that if we had a local deterministic theory, that would debunk it. Well, in 1994 is when binary mechanics was formulated. We had one. And so the only way to show that there is supraluminal communication would be to debunk binary mechanics. And I hope somebody here can debunk it. but no one has so far.
Thanks for the clarification. So entanglement is maybe okay, but it's the superluminal communication Bell inequality aspect that you're debunking.
Yes, sir.
That's kind of cool.
Yes, sir.
Well, towards the end of I think last week's discussion, we raised, or I raised perhaps, the question of, say, gravitational interaction. Now, I don't actually use the term entanglement in my own analysis, but I conceive of an interaction. Now, say, theoretically, one has formulated an interaction between gravitational masses. For example, the stability of the solar system. If gravity had a finite slow speed, such as the speed of light, which is what the orthodox would say, you would get an unstable planetary system, and you'd actually get the thing spiraling out in a short period of time, maybe hundreds of years, that the whole thing would become unstable. So Laplace calculated that based on the known stability of planetary orbits, the speed of gravitational interaction has to be at least 10 to the power of 8 that of light. Now, that was maybe early in the 19th century. More recently, the American physicist Tom Van Flandern, who's deceased now, but I'm going back some years, performed some experiments, and he actually plugged figures into the equations and so on. And his estimate is that the speed of gravity would be something like 2 times 10 to the power of 10 times the speed of light. Now, I'm just wondering how James would conceive of that type of exposition. I mean, it's a superluminal interaction, but it's not an entanglement per se. I mean, that's a quantum mechanical philosophical concept. So in binary mechanics, how do you conceive of that sort of experimentally based interaction?
Well, if I'm to respond to that, I would have to look at those papers specifically. As far as I know, the speed of light is sort of determines the ability to have action at a distance. Okay, so what you're saying is that there's gravitation someone has calculated that gravitational waves or effects are much faster than the speed of light, and as generally as we all know here, the conventional view is that gravitational effects are similar in their velocity as light. So I don't have a response to that at the moment. I guess specifically.
I would respond by saying that those experiments are just wrong.
Which experiments are wrong?
The ones showing that gravity travels at instantaneous speeds, those are just wrong. I think there's...
One might say that, but how do you get out of the theoretical argument that if gravity traveled at, say, the speed of light, you would notice an aberration precisely as we observe in the case of light, an aberration between, say, the position where the sun was 8.3 minutes ago and its actual position now. Well, we don't notice you can measure with an accelerometer the instantaneous position of say the sun. And you find that the gravitational effect is approximately where it is now, not where it was 8.3 minutes ago.
Well, I can give you my answer to that. I think we've discussed this before, and my answer is that most arguments, make the somewhat anti-intuitive presumption that the Earth is still and the sun is moving around the Earth, basically. That's why they say there's an actual angular difference. But the real situation is that the sun is stationary relative to the Earth. It is the Earth which is orbiting the sun. And if you think about the gravity waves coming out of the Earth, they are completely symmetric around the orbit of the Earth. Therefore, we would expect, I think at least I would expect, that basically the gravity that left the sun 8.5 minutes ago is exactly the gravity which is hitting us right now, because it's symmetric. It's basically symmetric. Now, maybe you might be able to find some difference because the Earth has slightly elliptical orbit. Maybe you might see, I don't know, some kind of, but effectively, the force of gravity is instantaneous because it's already had the 8.5 minutes to get out into the space where the Earth is traveling through, right? So we would expect that the force is effectively instantaneous, right? But it's not instantaneous. It's only instantaneous. It only appears that way because at the place where the Earth is in orbit, the gravity wave that is now hitting the Earth, which was generated 8.5 minutes ago, is exactly the same as the one that is coming out of the sun right now. It's geometrically the same. So if it's geometrically the same, then the 8 minutes don't matter. So, that's how I explain it.
It's a good attempt. But, with respect, Franklin, I think you're going to have to explain a number of experiments, maybe about 8 or 9 experiments, which have been done. For example, another one, I don't have Van Flanders' paper in front of me. I can get it if necessary. But one experiment is he shows that there is a difference in time between the maximum solar eclipse. If you have a total solar eclipse where the moon is covering the face of the sun, there's a difference in time. I think it's 38 seconds. It depends on the speed of the moon. Difference between the time of maximum optical eclipse and force eclipse by measured with accelerometers. In other words, when the moon, Earth, and sun are in a line, I think there's a 38-second difference, and that depends on the speed of the moon. So it's showing the difference between the aberration of light and the aberration of gravity. And I think your theory is going to have to explain about 8 or 9 experiments. You might look at that at your leisure.
It might. I mean, I haven't looked at this to any great degree, but I would rule out all
Hello, you're frozen there.
Yeah, he's frozen.
Yeah, he's frozen to all of us. Okay. That must be the gravity gremlins getting at him.
It could be that gravity instantaneously has somehow affected his ability to move.
Yes, I was thinking along similar lines. Because sometimes when we say unorthodox things and we say it's
there's
the
Bill Lucas.
mainstream police stopping us.
Yeah, I got cut off there for a little bit there.
Okay.
But I was trying to explain that I would rule out all experiments done in static gravitational fields. Because what you're really looking for is like the sudden appearance of something. Like you make a ball suddenly appear in space, and then you have to go and measure its appearance, right? You cannot ever do any gravitational speed experiments where you've got one thing moving around a stationary gravitational field, right? I would just categorically rule out. Now, the only other experiment which comes to my mind are the LIGO, say, black hole detection experiments, where they have multiple of these things around the world, like 2 or 3 of them, and the signal that they're getting comes in at different times. It's a small amount, but that shows that, if they are actually measuring a gravity wave, and I'm not sure they are, but If they are, then that thing is definitely traveling at the speed of light. And that would be an example of experiment where something just suddenly appears, and then you measure the speed of the wave as it reaches you. So LIGO has at least 2 sites. They see the signal coming in at different times. If gravity traveled instantaneously, then we would see those signals at exactly the same time. And that's definitely not the case.
Well, I always make a distinction. I highlight this between gravity waves and gravitational interaction. I mean, I'm not sure of those LIGO experiments. I'm prepared to take them at their face value, that maybe it's roughly the speed of light, or it's a bit greater, or it's a bit less, or it's equal to the speed of light. But those are gravity waves. Like if you have gravitational force variation in the ether.
Well, that is a gravitational wave.
Yes, that's gravitational wave. And that would probably, on a theoretical basis, travel at roughly the speed of light, of the order of the speed of light. There's no surprise in that. But that's quite different from a gravitational force. I mean, another example would be maybe in another area, like an electrostatic field. Experiments, and I need to do more work on this, but experiments seem to show that the setting up of an electrostatic field takes place maybe orders of magnitude greater than the speed of light. Now, that doesn't mean that electromagnetic radiation travels faster than the speed of light. That travels at the speed of light. That's the wave generated by the variations in these electric fields and magnetic fields.
Well, that one I had not heard about. I mean, I heard about gravity being measured as instantaneous, but not the electrical field being measured as instantaneous. So once again, I don't know. Me personally, since I think gravity and the electrical field travels on an electromagnetic type wave, my personal opinion is that it must travel at the speed of light because it's an electromagnetic wave. But, that's just me. But let's get back to the topic of our conversation here, which is entanglement. So, Ian, I wanted to ask you, what did you think of James' exposition here on entanglement? Did you understand? Because I know there are just a lot of buzzwords that go along. This as he talked about freedom, he talked about belt inequality, he talked about determinism. Did any of that make any sense to you? Or if it didn't, what do you not understand?
Well, I thought I was following it all right, but I might have to ask James's leave here. I might have to ask him maybe later or to summarize, because I'm not quite sure. He seemed to be saying contradictory things at certain times, but so I'm not quite sure, what he was getting at. But
give me an example of one of those contradictions, because I think it's very important, because it all seems like contradictions to me. So
yeah, okay. Well, I mean, that's
one
of the reasons I raised this point we've just been arguing about, because James seemed to counteract the possibility of superluminal interaction. But then he appeared to be accepting a sort of determinism. So and I mean, my position, maybe I'm just looking at it from my own point of view, but my position would be I accept determinism, but I also accept superluminal interaction, and I think maybe they're related. You see, it seemed to me that a lot of these quantum mechanical views, the conventional views, they have in common with relativity theory the centrality of the observer. So they're looking at it from the observer's point of view. As you yourself said earlier about the cat experiment and so on, Franklin, they're not merely saying, oh, we don't know what the situation is. They're saying that it's not decided. It takes the observer to look at it before it actually happens. And that really philosophically goes back to Berkeley, maybe in the 18th century, with his whole philosophy of idealism, that nothing exists until it's actually perceived. so you know the story of it, that Dr. Johnson was walking with his biographer James Boswell one day, and he was explaining Berkeley's idea that the tree doesn't exist until somebody perceives it. And Johnson is poo-pooing it, and Boswell says, "Well, but you cannot disprove his theory." So Johnson is passing a lamppost, and he gives the lamppost an almighty kick with his foot, and he said, "I refute it thus." But it seems to be harking back to this idea of idealism. Now, James seemed to be counteracting that, and the binary mechanics business, which I need to study more, seems to counter that to a large extent, which seems to be consistent with the way I would look at it. And I'm not looking at it from the same vantage point of this sort of quantization of space and time, but that seems in line with my ideas. And yet, the sort of prohibition of superluminal interaction, as distinct from, say, velocities of waves, seem to be, on the one side it was one thing, and then one side another.
Well, I don't think that.
Well, if I may respond to that.
Well, let me see if I can answer.
Respond to what Ian said.
Well, let me see if I can respond to what Ian said, and then you can respond to what Ian said, or else I'll respond about what I think you would respond, and then we'll see whether you say the same thing. How about that? But I would say that the topic of superluminal communication is kind of a separate topic from entanglement per se. I think James would say that entanglement does not work by superluminal speed. But that doesn't rule out that superluminal things can't happen. So, for example, gravity could still travel at superluminal speeds, but that's not an example of entanglement. Okay, so that's what I think James would say. So let's see what James would say.
Okay, well, in response to what Ian said and what Franklin just said, I must point out that the velocity of light in binary mechanics is equal to what I call bit velocity divided by pi. Because so bit velocity is pi times faster than the speed of light. Now, what is bit velocity defined as? If you go to the binary mechanics fact on my website, you'll see there's a little chart there that shows that bit velocity is actually the length constant, which is the size of the quanta loci in space, in the quantized model of space in binary mechanics, divided by the quantized time value. That's your bit velocity. In other words, a single quanta can only move 1 unit of distance in 1 unit of quantized time, and that's called bit velocity, and it's pi times the speed of light. So in other words, I'm opening the door with regard to what Ian said to maybe some things might appear to be going faster than the speed of light. In fact, I have a paper showing that certain configurations of quanta can produce motion faster than the speed of light, motion of quanta faster than the speed of light. And in my speed of light studies, they show this shows up as a few quanta appearing before the main wavefront of a light signal being transmitted from one side of a simulated volume to another side of a simulated volume. So it's a demonstrable effect. So I guess that's the little caveat I'd like to put in terms of what Ian said, that in other words, some faster than light transmission of information is possible. But it's not much faster. It's just slightly faster. It's not like orders of magnitude faster, okay?
So maybe, but I think maybe part of my confusion was if you have an interaction between particles, say something happens in one side of the universe, and then you're talking about its effect on something on the other side, very millions of light years away or something. Well, if this thing is only going slightly faster than the speed of light, you're going to have millions of years with no effect from this cause. You know, which seems to be, well, I mean, ultimately it has determined that something would happen, but I mean, it's you know, you have eons of time going on, and there's been no effect. Whereas if this thing is really traveling at very, very high speed,
Ian, you're arguing in favor of cause and effect in science, and
I am, James. I'm aware of that.
Contradicts what you were saying.
No,
yeah, okay. Well, I agree with that.
It's just the mechanism. Maybe we have difficulties. Maybe combining them or reconciling them, but we agree on that basic principle.
Yeah, I think a lot of us, you know, that's the intuition that there is cause and there is effect. And I think a lot of people think that the state of something doesn't depend on us looking at it. But I think literally this is the confusion that is caused here, because quantum mechanics wants to believe so vehemently that things do not take on their state until we look at them. So, you know, I looked at like what Bell's theorem is. You know, James mentioned Bell's theorem, and it's called an inequality theorem, but all that Bell's theorem is saying is that according to quantum mechanics, that if we look at something, that there's a probability that it must, you know, if there's something can be in two states, there must be some probability that it is in either of those states. So, and Bell's theorem is saying that quantum mechanics cannot be right, or that it's limited because, or that it contradicts what we would normally think. But I actually don't think we've actually seen any experiments showing this, I don't know, inequality, that they're saying that if quantum mechanics were true, then if we were to look at, you know, if I take something like, you know, this system of bricks, which is red and blue, and I split them up. So quantum mechanics is saying we don't know which brick is which until I look at, you know, one of these bricks and see that it's blue. That until I open my hand, it could have been red or blue. So Bell's inequality is saying that there has to be some chance that when I open my hand, you know, this is not going to be a red brick. It's going to be a blue brick, right? That's what quantum mechanics says. But it seems like, you know, all the experiments that James, say, referred to show that that concept is just not right. That every single time they do these experiments, that it turns out that when I see that there's the red brick here, there's the blue brick there. It's always that way, right? That's what we would obviously expect. But quantum mechanics is desperately trying to say that should be a red brick every once in a while, right? Because it's not determined until I actually look at it, right? So I think that's what Bell's theorem is trying to say. So let me try and share.
Well, let me clarify that. The Bell's theorem is saying that is used to determine supraluminal effects. Okay, and and so that's what it's used for. All right, and what you're saying is sort of the opposite. It's trying to show, but that there are supraluminal effects, and various observers over the decades have found various loopholes which could explain the results without there being supraluminal communication faster than the speed of light, and a lot faster. And what has happened is that Bell himself said that the the greatest loophole at all would be a deterministic theory involving local realism, which is what binary mechanics is. Now, binary mechanics did not exist when Einstein and Rosen and the other guy did their paper, on this spooky action at the distance. But in 1994, it did exist, and so there we have the fact. In order to show the supraluminal communication, you have to debunk binary mechanics. It's that simple. And there is no other local realism theory that I'm aware of. So there is no other one. There is no competition. There's only one that I know.
In all fairness, binary mechanics is not an accepted mainstream theory. So it's, an interesting argument, but it's like me saying that the Easter Bunny exists and therefore quantum entanglement doesn't exist either. So, it's although I don't think that, what's really at stake here,
I don't think the analogy is appropriate at all. That analogy makes no sense whatsoever.
Yeah, it doesn't, because it's not a fair logical.
Well, then why did you just say it? You did that, in order to detract from the point I was making. And now you're saying, no, I didn't say that.
Okay, well, maybe I said it wrong. But I will try to say it in a better way, which is that unaccepted theories from dissidents are about as good as fairy tales. Okay, that's the way I'll say it. And so we should accept all dissident theories, even my own, as if they were fairy tales. So we really can't use that as an argument against mainstream, since everything that we're saying is basically a fairy tale that we made up in our own head. So to the extent that, we're not any kind of authority, that we don't have any experiments backing us up, blah, 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 we can say that, but it doesn't, it has the veracity of a fairy tale. That would be my argument there. And, we're all guilty of that, so.
But by the way, just getting back for a moment to the classical philosophical view of idealism, I think the Berkeley's system was basically arguably objective in that the observer was always God, if you like. So there's a little ditty actually which sort of parodies that. It says, you may have heard this: there was a young man who said God must think it exceedingly odd if he sees that this tree will continue to be when there's no one about in the quad. That's Berkeley's philosophy. And then the answer is, dear sir, your amazement is odd. I am always about in the quad. And that's why this tree will continue to be, since observed by yours faithfully, God. Now, the modern QM system would say, and I suppose people were parodying it with the Schrodinger's cat, but they would say, well, there's no way of checking whether the cat is alive or dead. In fact, it isn't alive or dead. It's both or neither. It probably wouldn't say, well, there's some force in nature which observes it, some objective force or something like that. It would say that it's indeterminate. That hence quantum computers. You have a system where you don't have the bits 0 or 1. You don't have the thing magnetized or not magnetized. They're simultaneously carrying information in both states. I think that's why they're called quantum computers.
Well, what Ian just said, in my opinion, the use of the term indeterminate. What is indeterminate is not state of the system. What is indeterminate is our knowledge of the state of the system, with regard to the cat or whatever. And so the physicists today confuse these two usages of the term indeterminate, okay? In a local realism theory, the one that Einstein called for, in order to debunk the supraluminal communication action, a spooky action at a distance, he would say, involves a deterministic system. In other words, what is indeterminate in legacy quantum theory and physicists' minds is what they know, not what actually is. And that's where the confusion, I think, comes from. And it's actually egocentric to be saying, well, the world is indeterminate in X, Y, or Z fashion, for example, a cat either dead or alive, or both, or whatever, versus saying, I don't know what the state of the cat is, because he's in a closed box or whatever reason there is. So it's very, very important to make this distinction in this usage of the term indeterminate, because physicists simply throw up their hands and say, well, we know everything because really the world doesn't know what's going on. The world is indeterminate. Well, no. The only thing that's indeterminate for these physicists, dear friends, is what they know about the world. That's what's indeterminate, and only that. Thank you.
Hey, I'm going to do an entanglement experiment. Okay? I just thought I could do it. So I've got my blue brick and I have my red brick, right? So I'm going to shake them up in my hand, and I'm going to take one, put one in one hand and the other in the other hand. Okay. Now, according to quantum mechanics, what's in my hand? Is that a red brick or a blue brick? Okay, according to quantum mechanics, that's indeterminate, right? As James says. Now, is
only
that
in your mind is it
okay?
Indeterminate?
Right? It's only
It is the color that it is, but it's only in your mind.
Right?
No,
but quantum mechanics,
perhaps incorrectly, we concede that, but quantum mechanics would say it doesn't have any objective existence or not. It's not merely that we don't know about it. That's what it says. Now we concede that this is probably erroneous, but that's what conventional quantum mechanics says.
Yeah, so we're saying that's wrong because that's obviously, not that's obviously not the case here. Okay, so when I open my hand, I say, "Aha, that is a blue brick." Then, intuitively, I know what's in my other hand. It's going to be a red brick, right? But quantum mechanics,
because you started with two different bricks.
But
Because
quantum
you started
mechanics
with two.
would say
If you started with two of the same color, they
well,
would be the same.
This is what quantum mechanics. Let me explain what quantum mechanics is going to say. Quantum mechanics, it says that as soon as I reveal the blue brick, I have collapsed its waveform, and it has to instantly communicate to my other hand and turn this into a red brick. Now that's what quantum mechanics is
That's
saying.
magic.
See,
Yeah, that's
so
for
I think
nightclubs. That's what you do in a nightclub. You don't do that in a physics classroom. You do that in a nightclub.
No, apparently
As a magic
this
trick.
is the main thing about entanglement. That's what we're trying to point out. As silly as entanglement might seem to us, especially in this little demonstration, it's like, okay, which one is it? I could
But there's
perform
no
this experiment a million times.
superluminal.
I could
There's
perform
no
this experiment a million
superluminal
times.
communication,
This is exactly-
Franklin.
James, I'm trying to explain to people what the deal is.
They
okay?
separated. They separated. Are you saying that they separated at greater than the speed of light? Well, if they separated at the speed of light, there is no superluminal. If you started out with blocks of two different colors, they're going to be two different colors when, after they travel the distance between your right and your left hand. There's no superluminal communication in your example.
Yes, but I'm arguing that is what quantum mechanics would say. That's what they saying entanglement is, which in this example is, patently false, right? It's just obvious what's going on, right? And I think in the historical context, Einstein also thought that was wrong, right? So that's why Einstein was never convinced of quantum mechanical effects of this sort. He was never convinced there was superluminal
But I think it's even worse than that. I mean, you've given this example where we just have possibility blue and red and the collapse of the wave function. But I think the whole of quantum mechanics is based on the premise that nothing is 100% probable or certain because it's not determined. So in other words, even though you started off with one red and one blue, and even though you've established which is the red, you're not sure the other one is blue. It's just the preponderant probability is that it is blue because its atoms and its whole constitution are such that it absorbs all other wavelengths but blue. But actually, it could be red as well.
Well, I think that's Bell's theorem, actually, which is what you just said, which is that occasionally when I open my hand and I see that there's a blue brick, that occasionally when I open my hand, there should be a blue brick.
Yes.
Right. Now, that is the kind of actual experiment that we would need, right? To show that when I do this, when I see blue, I open up my other hand and it's blue because quantum mechanics says that that's possible, right? Although all the experiments that we see always end up like this. It's like, I see blue, therefore I know that's red. That they're always entangled in that way.
Well,
so
they say you need to do the experiment billions and billions of times, and you might find out that it's blue on one occasion, but all the other times it's red.
Yeah, they might. Now, I did find a relatively short video, so I wanted to show this to you guys. That just kind of goes over this whole entanglement thing. I thought it was kind of interesting. So let me see if I can share that with you. So let's see here. So this actually saying that could disprove Einstein's theory. Well, Einstein meaning that the world was deterministic, right? Although I don't think that this experiment actually does that. So I'll let you guys watch this and you see what you think here.
A genius. The man conceived of special and general relativity, theories that have been breaking brains since the early 1900s. But when it came to the idea that two particles can be entangled and an effect on one could be instantaneously felt by the other, even over vast distances, well, for Einstein, that was simply unbelievable. He dubbed it spooky action at a distance and went to his grave a skeptic. But since then, quantum entanglement has been demonstrated time and again. And now, for the first time ever, we've taken a picture of it. To achieve this, researchers from the University of Glasgow shot an ultraviolet laser at a crystal, which broke apart some of the photons from the beam, creating two entangled photons. When particles are entangled, their properties or states, like spin or phase polarization, will be linked. But until they are measured, those properties will remain in superposition, meaning it can be in multiple states at once. Observing one particle will make it take on one state, while at the same exact moment, its entangled twin will take on the opposite state. The entangled property of the photons the researchers chose to observe was their phase. Remember that photons can behave as both particles and waves, and a photon's phase is where it is in its wave oscillation. Photons that are in step or in phase can amplify each other to give a brighter intensity, and out of phase they can cancel each other out to give darkness. Once these entangled photons were created, they were split and sent on different paths. Down one path, the scientists set up a filter that would limit the photon to one of four different phases. Passing through this filter is effectively the same as observing the photon's phase. So as soon as its phase was determined, its entangled partner traveling down the other path would take on the opposite. Finally, when the two entangled photons in opposite phases were simultaneously detected, a super-sensitive camera capable of detecting individual photons would take a picture. Scientists repeated this until they could build up an image of the entangled photons, allowing the waves to amplify and cancel each other out. And without further ado, here it is. The photons look like eyes, so spooky definitely seems like the right word for what we're looking at. If you look closely, you'll notice two gaps in the circle where the intensity smoothly drops off to zero. That's the phase the scientists were measuring. And this picture further counters how Einstein thought quantum entanglement could work. To make entanglement jibe with classical descriptions of physics, he proposed so-called hidden variables that would act as a messenger between entangled pairs. When he proposed this, no one knew how to test if a hidden variable was at play or if the quantum world was just really weird. In 1964, almost a decade after Einstein's death, physicist John Bell came up with a theorem that can distinguish between Einstein's proposed hidden variable explanation of spooky action and quantum mechanics' entanglement explanation. These statements are known as Bell's inequalities, and years after he devised them, they were tested and contradicted Einstein's idea of a hidden variable. This photo adds to the pile of evidence against Einstein, violating Bell's inequality that assumes the hidden variable interpretation. So, now you have a picture to put in your locker next to that photo you have of Einstein with his tongue out. It may serve as a nice reminder that your name can literally be synonymous with the word genius, and you can still get stumped sometimes. It's a good thing quantum entanglement is real because it's key to a quantum computer. If you want to see how close we are to finally building one, check out this Focal Point episode all about it. So what's the coolest picture you think science has ever produced? This entangled photon picture, a black hole, or something else? Let us know in the comments. Be sure to subscribe while you're down there, and I'll see you next time on Seeker.
Well, the whole thing is like propaganda. He's in a local realism deterministic system. If the two photons were like your red and blue blocks that Franklin has handy, of course they're going to maintain. They can maintain their properties over time. And so it would appear that there's supraluminal communication when in fact they've just maintained their property over time. Now, the Bell inequality experiments assume that they have no property until they're looked at, which is a complete absurdity. So you see that this young man in this video is talking pure nonsense as if it were some important point to be made in terms of how our physical world works. And so that's my little review of that video. And of course, most of the videos like that on YouTube, they wouldn't be there if they were actually accurate. Okay? YouTube bans anything that's accurate. So is that a YouTube video? I mean, that goes without saying that it's probably
video. It's the source of all truth, just like Wikipedia is, right? Okay. But see, this is the problem I have with that video, in that this experiment shows that entanglement can happen. It's like, duh. Okay, that's not in question here, I guess, right? That entanglement can happen. That you have the red and blue brick. If you open up the one hand, you know what the other one is. I mean, that's. But that didn't disprove what Einstein was saying. So Einstein's saying is that there's this thing called hidden variables, right? And that there's something inherent about the particle itself which carries the information, right? So just like, in this case, what's the hidden variable? The hidden variable is that there's a die in my Lego bricks. I mean, my Lego bricks would probably all be white or whatever. But there's a die in the Lego bricks that makes one of them red.
The hidden variable, Franklin, is that you have that they remain red and blue.
Yes,
The
that's
hidden
what
variable,
I'm saying.
sorry to interrupt you, sir, but they remain red and blue. And so when they're separated, if you know one's red and one's blue, as you have been saying, if you look at one, you know the color of the other. In a local realism theory, you don't need any supraluminal communication whatsoever.
Yeah, and that was
They start out red and blue, and they remain red and blue. See, what they're trying to say is we don't know what they start out as. One might be red or blue, and the other one might be red or blue. But in this case, we know that one is red and one is blue, for sure.
Yeah, but I think
And so that's what binary mechanics
away from You're drifting away
variable
from the
is
main
just-
point here. Okay.
Okay.
But the main point here is that Einstein thought that there was these hidden variables, like in this case, the hidden variable is the ink in the brick, and that when we see one, we know the other. Now, the thing is that I don't think anything in that video disproved that, right? They showed entanglement happening. That that when they measured the phase of one, they get the phase of the other. They took a picture of it. They recovered the two sides of the picture, I guess, to show that they were entangled, right? And then at the very end, he takes one sentence saying that, this is in contradiction to Bell's inequality. It's like, how, right? He makes that one main conclusion, but there's nothing backing it up at all, right? He just says it.
It's interesting to note that the mainstream view and the preponderance of videos on YouTube and papers coming out every day, whenever they deal with the conflict between Einstein and, say, Niels Bohr or the quantum physicists, they come out on the side of the latter. They say Einstein was the most brilliant man we've ever had, but he was wrong on this occasion, and Bohr is right, or the quantum physicists are right, or Schrodinger is right, and so on. Conversely, when they're dealing with relativity, they say, here's another piece of evidence to show that Einstein was right. He was totally right there. So there's a sort of an orthodoxy there, which we have discussed before, and is biasing the interpretations. And I would submit that is why you and all of us are finding it difficult to follow the logic of these expositions.
Let's see here. Bill's got something here. We haven't let Bill talk here. Let's say, so you're saying something about that the electromagnetic field falsifies quantum mechanics? In what way?
Quantum mechanics assumes that the electromagnetic field consists of independent pieces, and they can mix and match and all that in arbitrary manner. But the measurements that were made at University of California at Berkeley by William Hooper and others shows that there is a tensile strength of the electromagnetic field, and the electromagnetic field extends to all the universe. So that means that everything in the universe is interconnected by the tensile strength. And so these ideas that we're talking about in quantum mechanics have no basis in reality.
But what do you mean? Because, we just saw an experiment where they split up a beam of light so that it was in a particular phase, and then they measured them. I mean, what's wrong with that?
Those beams were all connected together, even though they were split up. The electromagnetic field is still connecting all of them together. So that's what you see. And
I mean, in what way? I mean, I could say that with my Lego brick experiment. I could say that the red brick is all still connected to the blue brick through the electromagnetic field. And I would say, so what? That's obvious for anything. That could be between my mouse and my blue brick. And, it's just a truism.
And
right?
Everywhere in the universe, everything is interconnected. There's nothing that's independent. There's nothing that can be changed by your observation unless your observation interferes with its characteristic.
See, now there you said something that was, interesting and different, which is that. But that really doesn't rely on, the things being interconnected, I don't think.
Yeah.
I mean, that things are interconnected, I think is kind of obvious.
Yeah, it is. But where quantum mechanics says, no, they're not interconnected.
I don't know that quantum mechanics has anything to say whether they're connected or not. I don't know.
Sure, it does, because the quantum wave function doesn't allow interconnectedness. That's the whole idea of quantum mechanics. is that. And by the way, in order to accept quantum mechanics, relativity theory, the theory of the atom and the nucleus and elementary particles, we had to abandon the scientific method that had been used for thousands of years because they falsified those theories. And so what we did is we invented the existential scientific method, which is based on the hypothesis and doing experiments. And then we ran into trouble with different fields. So we went to the postmodern philosophy of science, which says it's the same as the existential, but each field of science is independent from the other. So if you find something in one field, like chemists found that gravity was electromagnetic in origin, they completely ignore that in the field, in the silo of physics. And
can we get back to the topic at hand, which is quantum entanglement? So specifically, maybe you're saying something like, even if these two particles were interacting, they're interacting because they're connected, right? Is that what you're trying to say?
Well, the electromagnetic field has tensile strength, and that means you never break the interconnection. And
you're saying that in that experiment, that the photons were still connected, right?
That's right. The
So that would
field.
be your
The
main
photon
point.
the photon is a disturbance in the field. The field is what has the interconnectedness and has the tensile strength.
So perhaps your explanation is that when the photons were split, they never were actually split. There was always something between them, and then when they measured them separately, it's like they were still connected.
That's right.
So that may be perhaps your explanation.
That's right. Right.
Okay, I think that kind of brings out what is specific about there being something in space that constantly connects everything.
And and what is very interesting is that because of that property of the electromagnetic field, all forces in nature have to be electromagnetic because of the tensile strength. And when people like myself have derived the force of gravity from electrodynamics, showing that it's the force between vibrating neutral electric multipoles like dipoles, quadrupoles, octopoles, which you find in atoms, between looking at electrons and protons. And when you see that, we're able to, the force of gravity we derive is able to explain all observed gravitational phenomena without having to invent dark matter and dark energy comprising 96%
Let me ask you a
of the
question
universe.
then, right?
So,
if all the forces are electromagnetic, then what is the force that are involved in Newtonian collisions? So when I'm on a billiard ball and I fire a billiard ball at another ball and it bounces off, that's a force, right?
Yeah,
Definitely, that's a force.
yeah.
I would claim that's not electromagnetic. What do you say?
Well, I've been able to derive the force of inertia and the force of gravity and define inertial mass and gravitational mass.
Yeah, but you're not
terms of
answering my question.
electrodynamics alone.
You're diverting. You're not answering my
Right.
question. I'm saying that there is another force. It's the force of elastic collisions.
No,
and that's
what I'm
not
saying-
an electromagnetic force.
I'm saying from electrodynamics, you can define all of the forces you see. And from the NIST study
and I'm
of...
saying, no, I don't think you can. None of those forces explain, why is it when a hard object hits another hard object with the kinetic energy that it changes its trajectory? I'm saying, okay, I'm claiming that is not an electromagnetic force, right? So I'm saying that's not gravity, that's not electromagnetism, that's not any of those field forces at all. That's Newtonian mechanics. So I'm saying that you're wrong.
But logic says that's impossible, that if you have a field that goes throughout the whole universe and it's electromagnetic and it has tensile strength, it has to explain all phenomena on all size scales. And that's what we find is true when we actually do the investigation and look at the data that's measured.
But you haven't refuted what I'm trying to catch you at, which is I'm saying that kinetic energy collisions are not explainable by electromagnetic forces.
Sure. What
No,
makes
they're not.
what makes two things bounce off of one another when they hit? It's the repulsion, electromagnetic repulsion, due to the charges in those items.
No,
And-
I would say it's not. Now, maybe that's just our point of disagreement here.
But you see, you cannot explain what is mass.
Sure, I can
You
explain what mass
cannot
is.
explain
I
the
know
difference
exactly
between
what mass is.
gravitational mass and inertial mass because you don't have a detailed theory.
Yes, I do have a detailed theory. Of course, I know what mass is. Mass is resistance, the resistance of a guest particle going through the medium, which is space. That's mass. That's
No, you're not explaining what causes the resistance. You don't have an explanation. You're just
Yes,
using
I do have an
a
explanation.
constant.
I would explain that the fundamental force, and this is why I'm bringing this up, that the fundamental force is the force of Newtonian collision. That when you have anything going through anything, just like if you had a children's ball pit and you tried to push another basketball through that, of course you're going to get collisions and you're going to get resistance, right?
Well, you've
That's
got
the
to
nature of the
explain
resistance.
the Russian data by Dmitriev, and he showed that if he changed the temperature of any item, its mass changes.
Yes, that would be a direct prediction that the mass depends upon the environment. So that definitely something. I
No,
would
not
predict.
the environment. This, we put this in a vacuum and we change the temperature, and what happens is the mass changes because it's electromagnetic in origin.
Yes, it is electromagnetic in origin. See, I would agree
Yes.
with that. I
And it
would
can
say
be
that,
defined without using the term M. We can just write down what M equals in terms of electrodynamics.
Yeah, I mean, I would totally agree with you that all the forces, gravitational, magnetic, and the weak and the strong force just don't exist. So really, there's only the magnetic and gravitational force. That those are all electromagnetic in origin. But I would argue that the electromagnetic force itself has its origin in collision forces. That's would be my claim, and that's why I'm saying that when you say that everything is electromagnetic in force, I'm saying no, because electromagnetic itself.
But
force
if you were
itself has,
right about
a
collision,
hierarchy.
if you were right about the collisions producing the force, you would not have a tensile strength.
Oh,
to the
sure
field.
you would. Why wouldn't you have a tensile strength? That's like
The tensile
the only
strength
thing you need to
cannot be demonstrated by collisions.
all you need to have, anything to have in tensile strength is something which is space filling, right? Like my stapler here, it fills space. And when I try and pull it apart, it has tensile strength because it's space filling and the particles that it's made out of are slightly attracting. That's the only thing required for tensile strength. So, as long as space is filled with some continuous substance that has some attractive ability, then yeah, that's tensile strength. I mean, and I have no problem with saying that there is tensile strength in space. It's absolutely necessary in order to propagate a mechanical wave. Certainly, so
Well,
there's got to be 100%.
there's another
connection.
property of tensile strength of the field that you don't seem to realize, and that is you cannot cut the field.
Well, of
But I
course you
can
can't
cut a
get
beam
the
of
field.
particles, and I can change the force. I can
If I
interfere
take a
with it.
cup of water, can I cut the water? Not really, because as soon as you try and cut it, it'll come and fill every space that's in it, right? Even though we know what that is. So it's like, I don't know that that's an argument.
Well, I can make with an accelerator. I can make a beam of particles, and it produces a force, and it has mass, and all that stuff. But I can cut the beam, but I can't cut the field.
Yeah, so
Field is
Exactly
something that's
what I would
uncuttable. In fact, the person who was attributed by the ancient Greeks and also the Indian Jains as being the greatest natural philosopher said that all matter is made of an uncuttable item, which we have reinterpreted since that time to be the chemical atom, but it isn't uncuttable. We can cut it up into pieces. We know we have electrons, protons.
Well, I mean, you've said that. You said there's the monad and antimonad, which is the actual uncuttable particle.
Yeah.
And that I would interpret as being the electron and the positron, which as far as we know is uncuttable.
But see, those particles are made of the field. There's no such thing as charge. Charge is an approximate way of saying what is the standard tensile strength in the area where we are of the universe. And so you have to see that. And we have logic taken out of our current scientific method. We do not falsify any of our theories in modern science because they disobey logic. They're false. We have.
Well, let's go back to the logic. I mean, what you just said, that charge doesn't exist, I would say is highly illogical, because we have definitely measured electrons have this property of charge. So for you to say that charge doesn't exist, would be illogical. Would you not agree?
No, I don't agree at all, because Arthur Compton and his last graduate student, Winston Bostick, they made solitons out of the field. Okay, so the soliton, and if you then measure the properties of the soliton, you say, oh, this is a toroidal ring and it's got charge going around the ring. But you made it out of the field, there was no charge. And so,
well, what field were they making out of? I mean, I've looked at these experiments. These were plasma experiments. And I've seen the pictures of the solitons. And it's like, okay, that proves that you can make smoke rings out of plasma. But that doesn't say anything about what an electron is, other than maybe that's a possible format of it. And these, as near as I can tell, these solitons they produce did not have the same properties as electrons, especially that of charge. So if you put two soliton rings and you put them together, two smoke rings, when they come together, rip each other apart, and they dissipate and disappear. Well, that's their nature. So that's why
I have published the theory of elementary particles, and I've shown that the electron consists of 3 solitons, and to show the structure of all the elementary particles. I show how they decay. I predict the mass of every elementary particle that has a mass. All these properties, which no other theory can do. And that's because they won't acknowledge the role of the electromagnetic field. And in quantum mechanics, the wave function really is an approximation to the electromagnetic field. And you see that many areas of science which are falsified if you use logic, but we have taken the logic out of the scientific method so that they cannot be falsified that way. And if you see that and you try to do science in terms of logic, and my book, The Universal Force, derived from a more perfect union of the axiomatic or logic and empirical scientific methods, you see how you do these things. But we have taken that logical part out. And I remember when I was fired at Catholic University for showing in a major meeting of the American Physical Society in Washington, D.C., I showed that the primary theorems of special and general relativity theory are all known to be false by experiment, but we didn't falsify the theory because it makes some predictions that are verified by experiment, and we're not using the scientific method that's based on logic. So we don't falsify theories anymore based on false assumptions. And so all these alternative theories we're looking at have false assumptions, but we don't pay attention to it. And,
well, let's see. I see we got some comments from Roger here. So, Roger, did you want to chime in on what you think about the current discussion here? I have to unmute you here. What would you like to remain not saying anything. But you have to unmute. There you go, Roger.
Hello,
Hello, Roger. So what do you think about the discussion going on here today?
can you hear me?
Oh, yes, we can.
Great, okay. Yeah, I was dealing with the quantum entanglement thing and the bit about the split between quantum mechanics and relativity. The problem with that was Einstein got his backing for relativity from the Royal Society. So, as Ian points out, that's sort of prestige. And then later on, Niels Bohr had the control of the money for research. So if you were agreeing with Niels Bohr, you were getting your funding for research. So that's where the quantum mechanics split came along. Einstein versus Bohr. Einstein had the prestige from being backed by the Royal Society for relativity, but Niels Bohr had the money for people who wanted to do research. So that's the split, really. And as Ian puts it, the difference, possible explanation for the difference is money and prestige. And that, I think, just covers the state of mainstream physics anyway. That's why you're never going to get any headway. You've got all the prestige backing relativity, and you've got all the money backing quantum mechanics. So you're never going to get any change now because of human nature on that issue. And then when you get onto something like quantum entanglement, what the mainstream sort of says about that is, well, that quantum entanglement agrees with quantum mechanics. And the problem was with relativity and the locality issue, but they found a way of interpreting relativity which they say agrees with entanglement. And so from their point of view, quantum entanglement, yeah, it agrees with quantum mechanics and it agrees with the way they want to interpret relativity. So
it disagrees with Einstein.
Sorry?
It disagrees with Einstein. See, this is the weird thing, right? Because you're saying anyone who believes in Einstein gets funded, but in this case, Einstein doesn't believe in quantum mechanics. And the people who are getting funded are the people who are trying to prove him wrong.
That's right. Einstein disagreed with quantum mechanics, but the experiment to test quantum mechanics versus relativity was the Bell experiment, Bell aspect, I think, did the experiment. But it's the quantum entanglement experiment, and that was a big clash between the two theories, and they found a way of interpreting relativity so it still agrees with the experiment. This is what they claim. You can disagree with what they claim, but that's what they claim.
Well, I didn't know there was any relationship between quantum entanglement and relativity. Is there such?
Well, the difference is what Einstein calls spooky action at a distance. If you got a quantum entanglement, then you've got what Einstein dismisses as spooky action at a distance, which he disagreed with. And so you've got all that philosophy behind that. You can sort of like take Einstein's view, but now they've decided they can think of relativity in a way which doesn't actually agree with what Einstein was saying about it. But if you try to pin them down on that, they won't be pinned down on that. I've got, when I went to an Einstein conference when they were honoring Einstein in 2015, they got one of the big Nobel Prize winners giving a talk, and he's saying they understand relativity now better than Einstein did. And I've put that video on the internet. And so that's their point of view. They're so arrogant. They sort of, Einstein said all this stuff about relativity, and now you got the Nobel Prize winning physicists, and they think they understand relativity better than Einstein. So you try to use quantum entanglement to show the difference between quantum physics and relativity, and no, they've moved the goalposts. Basically, it's logical fallacy of moving the goalposts. So that's where the position is at the moment. The mainstream believes quantum entanglement can be explained by their existing theories, and if that's the case, then there's no reason, in their point of view, for changing to any other theory. There's what they got now works. No need for a new theory. That's the way human nature does things. So
all I can say is I'm with Einstein, right? Okay.
well, you can say that. You can take their point of view, but the way the mainstream has taken it is it's gone that way, and so all us dissidents, you can sort of like say, well, or you come up with your own pet theory. You can come up 100 people, 100 dissidents, and you come up 100 different pet theories. But mainstream's not interested. They say we can understand things from what we've got already. Hence, there's no need for a new pet theory. And that is the block all the time on things. You've got to have an experiment which is not explainable by their existing theories, and then they then say, well, we need a new theory. But they're not going to go that way. They're always going to move the goalposts.
Well, of course they're going to move the goalposts. They're in charge of the game. They can do whatever they want. They can change the rules however they feel.
That's what they're always doing. They're moving the goalposts.
And history is written by the victors. So what can you say? Right?
Well, this is the same thing with when you go back to the Copernican revolution. You never really had to give up the Earth-centered theory. All you have to do is keep moving the goalposts. So there was no reason for changing. And it's exactly the same thing now. There's no reason for the mainstream to change their position. All they have to do is keep moving the goalposts.
Well, then how did we get that whole, heliocentric thing? Although some people say that theories only change because the older people die, pretty much.
Yes, yeah.
I mean, there's people who are denying plate tectonics, till the day they died.
Yeah. So it's really, I think, behind the scenes, it's money. And so people, if you want to cause a change in physics, you've got to have a lot of money and back an alternative.
Or maybe just to wait for everyone to die.
Yeah. Well, no, you've got to have money. People die in the distant movement all the time. And so they just die and get forgotten. You've got the big names like Louis Eason, Herbert Dingle, etc., etc. They just die, and the mainstream just forgets them. And if there was big money behind sort of people like that to carry on their legacy, then you would probably cause might have a chance of causing a change. But since there's no money behind any dissidents, and the dissidents can come up with hundreds of different theories, there's no backing behind what they're saying, and so mainstream has nothing to fear.
Yeah, mainstream has nothing to fear from us. I don't.
Yeah.
We're just in our own little sandbox here. So.
We can just talk around in circles. Nothing going to get anywhere.
But at least
I don't think it'll be merely people dying off, Franklin, because the new generation are being taught the new orthodoxies. And one very important thing is, you said, "Oh, I'm with Einstein and relativity, and I'm with the quantum physics, quantum theory." Well, what they're teaching the populace is that relativity works in giving our modern world great advantages in technology. All our GPS satellites and all our space probes and everything, that's all based on relativity. So you couldn't deny that. You're with technology. And then on the other hand, they say quantum theory is giving us all our electronic devices and all our digital devices and all our chips and software and so on. Sorry, I thought there was a bit of an echo. There's an echo.
Echoing here. I don't know where that's coming from. Let me just move off a few people here. Well, they do say that. It's like, we've got our satellites, and theoretically all of that has to do with quantum physics. Although I would say that, none of that has to do with, I don't know, entanglement, except that whole quantum computing thing that, Bob brought up that question. Does quantum computers actually use this superliminal entanglement to do its job. And I've always just been, I mean, I haven't done a whole lot of work on that, but this whole idea of a quantum computer just seems to be a method of generating grant money, as far as I can see. And that
and furthermore, I think it's using a nice fancy word. I mean, I could be very cynical and say perhaps they should have called it sort of a multiplexing computer, because really that's what it is. It's a para-multiplexing computer, but that would sound awkward. So if you call it quantum computer, goodness me, it's the most up to date and most complex unit, and therefore generates a lot of interest and income from it.
Yeah, I personally think it's a lie. So, you know, and because it's like, I'm thinking that, you know, they've got these really fancy looking things that are in super cold environments, and, you know, looks really, but, you know, at most they say they got like 16 quantum qubits in this gigantic refrigerator sized machine. And they haven't really showed it actually solving any actual problems, right? And I think if they did, you would see that a conventional computer could solve that problem, you know, faster anyway. So I just don't think that anyone's really shown anything that's that practical. So I think it's an entire lie, because I would say that if the quantum computer is relying on the superliminal communication of the entangled particles, then I would conclude that that just doesn't happen. I'm with Einstein. I'm saying that, you know, there are hidden variables and that the state of the particle is inherent in the particle, so that when I reveal the blue, I know that one's red. There's no mystery. There's no communication. There's really nothing. It was entangled from the time I picked the particles, right? So if I know that's blue, I know this one's red, 100%. I love to see that. It's red. What a surprise. Okay. Not really a surprise, but that, and I don't think, you know, in all the videos I've seen, that effect has been disproven, right? That you know, in some way, that if I look at the blue, then when I look at my other hand, it's blue, right? Because that's what quantum physics says. It's quantum. It could have been red, it could have been blue, so it should show up blue sometime, but it just doesn't happen. So, and all the experiments show the same thing that I'm showing, which is when you see the blue, they're related, they're correlated. Of course, they're correlated, and you can call that entanglement. But there's nothing really mysterious about it. There's no communications. You can't utilize that to do communications, because it's kind of implied that if you could get this quantum mechanics entanglement thing to work, that I could have a transmitter on Earth that's looking at this, you know, the state of like an electron, and then I could change that state of that electron, and then suddenly the entangled electron on the moon would change with it, and then I could communicate using that, right? They're saying, yeah, I could have superluminal communications, right? I could communicate between Mars and Earth and like instantaneously, rather than waiting, you know, the 8 hours it takes for the signal to go from Earth to the Mars. But and the mainstream popular media, you know, implies that very strongly, that you could use it for communications in a way like that. But, you know, obviously it's a lie, because if they had their particle and they had it on Earth, and then they sent the other particle to the moon, well, first of all, you can't change this particle. Okay, I've got this blue Lego brick. There's no way I can change this to a red Lego brick, right? And that's the same problem with the properties of these electrons. If you got a spin up electron, you know, you can't just turn it into a spin down electron either. So, I mean, how do you do that? And if I have a phase of a wave, it's like, I can't just change the phase of the wave, right? And that's an ephemeral thing, right? That doesn't even last through time. So you can't change this. So there's no way I can communicate that to my other brick and make it turn blue. It just can't happen. All you'd end up with is one on Earth, you'd have the blue brick, and on Mars, you'd have the red brick. And there's no way you can communicate using those two things. So, but I think we've come to our time is up. So I wanted to thank you know, James for coming on the show today, and, you know, bringing up this topic of quantum entanglement. So it seems that in bit mechanics, everything is quite deterministic. And because of that, things like quantum entanglement, just basically can't happen because everything is deterministic. And it doesn't matter if we look at something, what it, does that change its state? And that's what Einstein believed. Einstein believed that there is, on all of these experiments, there's just he called it hidden variables, although I think that's really bad terminology. I mean, that doesn't make any sense. That made it so that matches our intuitions that a particle has a property. It keeps that property no matter how far away it travels away, right? It doesn't matter when we look at it. It has that property. So, and so we did that, and we discussed, and I showed a video, trying to explain this quantum entanglement, and that was just like, I only showed that one because that was like the shortest video I could find. All the other videos are like 15 minutes long, but if you want to look at those, I would invite you to type in quantum entanglement in YouTube and get a much longer explanation. But like none of these things actually disprove Einstein's hidden variable explanation, although apparently, say, Bell's theorem is supposed to disprove it. But Bell's theorem is not an experiment, right? Bell's theorem is at best a thought experiment, I think. And it's just pointing out a contradiction and showing that probably quantum mechanics is wrong. I mean, just like shown in your cat example is supposed to show that quantum mechanics is wrong, that of course the cat is not both dead and alive. So that was supposed to show that quantum mechanics is wrong, but instead it's being shown as an example of how quantum mechanics works. And that, in fact, the cat is, in fact, dead or alive. No, that's ridiculous, which seems to be the trick that quantum mechanics and mainstream use. It's like when presented with a irrefutable refutation of your theory, like the Schrodinger cat, you just turn it around and make it act as evidence for your theory instead. Say, yeah, that's exactly what happens. That's or it would seem. And then I got into a little discussion with Bill. So Bill thinks that there is something between all particles. So if I have these entangled particles, there was always something connecting them together. So maybe Bill is probably okay with the one particle talking to the other, but although I'm still not really addressing the fact that whether the communication is instantaneous or not. And that was a point that Ian was trying to bring up, that there is some evidence for, in some instantaneous, say gravitational, there are some places where such instantaneous communications appear to exist. Although I don't know that has anything to do with, say, entanglement per se. There could be some other way that instantaneous communication could happen that doesn't have anything to do with entanglement, I suppose. And then but also related was a little discussion about, what makes up all the forces. So Bill made the claim that all forces are electromechanical. So we got in a little discussion about, I would say that physical collision forces are not explainable under the electromagnetic umbrella, although Bill's comeback was that that the reflection is due to the electric field. Although I would say no, I don't think it is, because neutrons don't have any electric field around them theoretically, and they bounce off each other. So I think that would be my response to that. Right? I'm still claiming that the electromagnetic interaction is actually an interaction caused by actually collisions, right? And that's the fundamental force, actually. The force of collisions, I guess, would be kind of the way I would try to say that. So you would have force of collisions, that generates electromagnetic forces, that generates magnetic and gravitational forces, I guess is how I would be my preference. But that's what we're here to discuss. We can discuss all our own theories. So thanks once again to James. And if you guys have another topic, please feel free to bring it up. But I think that will do it for this episode, and I'll see you next week then.